Okay, so here we are at chapter 10 of the combined science syllabus, combined science chemistry syllabus, okay, which is on oxidation and reduction. Together they form redox. Okay, so these are the success criteria for this chapter. We need to define, uh, in, and then we need to describe the use of aqueous potassium iodide and acidified potassium manganate, okay, in testing for oxidizing and reducing agents from the resulting color changes. Okay, they don't mean too much to you right now, but very quickly, just to simplify things, potassium iodide is Ki equals acidified potassium manganate is KMNO4. Okay, but we'll look at this later. Now, first thing first, let's jump into part A, okay, and break down what exactly is redox. So redox is actually a combination of the two words right before it. Read come from reduction. Ox come from oxidation. Okay, and what does that mean? That means that when we have redox, both reduction and oxidation, they occur simultaneously. That means they occur okay, a better word might be concurrently. They must occur at the same time. Okay, so we look at the first success criteria which we are going to jump into this in this video is oxygen gain or loss. How does that help us? Or rather, how is that useful to define redox? So redox reactions are actually the third class of reactions that you saw in this you see in this whole syllabus. Before that we just finished acid-base neutralization as a whole chapter, and we also come across precipitation reactions. For example, when we bubble carbon dioxide into lime water, it forms a precipitate that is a precipitation reaction. So now we have come to the third class, which is redox reactions. Okay, and redox reaction is also very commonly seen in real life. For example, the rusty nail is actually a redox reaction. Our dear Mona Lisa, okay, holding her the fire is also a okay. Why is it green? Is actually also a redox reaction. Now, moving on. In part A, okay, the first way to define a redox reaction is based on transfer of oxygen. Okay, and we break them down into oxidation and reduction. Oxidation is when a substance gains oxygen, and reduction is when the substance loses oxygen. Okay, so naturally you should be able to define this. Okay, so well, it's rarely tested because it's actually quite easy lah. But you should be able to answer things like define oxidation in terms of oxygen transfer, or define redox based on the transfer of oxygen. Okay, now let's look at an example to see how we use this definition to figure out who is oxidized and who is what is reduced. Okay, so let's look at this famous example, iron ore. How do we extract iron ore? Is through this reaction. Okay, with carbon monoxide. So if we look at Fe2O3, it will turn into simply Fe. So what happened to it? It lost oxygen. If it loses oxygen, if it lost oxygen, it is a reduction reaction. Okay, so this is a reduction. Okay, and for simplifying things, I'm going to write reduction as a bracket R and oxidation as a bracket O. Okay, so 3 carbon monoxide on the other hand. Okay, or rather we are just looking at carbon monoxide. It has reacted and formed carbon dioxide. It has gained oxygen. So this is an oxidation reaction. So carbon monoxide has gained oxygen and it has oxidized. Fe2O3 has lost oxygen and therefore it has been reduced. Okay, so you can now take some time to do exercise 1 and pause the video in between. Okay, so the answers for exercise 1 is from C to CO2 it has, wrong color. From C to CO2 it has gained oxygen. So it is C has been oxidized. From Cu to Cu it has lost oxygen. So this is a reduction. So reduced CuO, oxidized C. Zn to ZnO gained oxygen, so oxidized. PbO to Pb lost oxygen, so reduced. Okay, so Zn and PbO. Okay, moving on. For FeO to Fe, it has lost oxygen, so it is a reduction reaction. So FeO has been reduced. Carbon monoxide to carbon dioxide, so oxidized. CO. In this last exercise, question 5, we look at C carbon plus oxygen give you carbon dioxide. Now, carbon has obviously gained oxygen from C to CO2. It has gained oxygen, so it has oxidized. So C is here. Now the question is, who has been reduced? Oxygen, did it lose any oxygen? It did not lose any oxygen. Okay, so now the problem is when we have reduction, we must have oxidation. They come as a pair. They are never apart. So when there is oxidation, there must be reduction. Okay, so therefore oxygen must have been reduced. So oxygen has been reduced. So this also tells us, hey, this also leads us to thinking, actually what happened is this definition all encompassing? It is not. Okay, because not all redox reaction fits into this definition. So okay, so reduction occurred even though the substance did not lose oxygen. Okay, so From question 5, perhaps there's some other better definitions, okay, and that's why in the course of history there are a total of the 4 definitions to define redox reactions. Okay, so that is all for redox definition based on oxygen transfer.